Yes.
Are you accepting any ads?
Yes. To accept, to be added to the course, you have to do two things. You have to send me the answer to the prerequisite quiz, which you should do as quickly as possible, and you also have to make sure that you get me homework 2 on Monday. I don't want anyone to fall behind here. So look at the prerequisite quiz. If you think that's a piece of cake, do it. If you think it's not, maybe not this semester. All right. Other questions? Yes?
When do we get our grades for homework 1?
Good question. The grader said he had graded them, and then he sent me an empty zip file. So I'm sure we'll get past that issue. I think he was under the impression that he was going to add the things directly to your repos. Yeah. So it's already a good thing if you could make sure that you add him as a collaborator. But I actually wanted, because it's his first time, I wanted to see what he was doing first. So we'll have it straightened out. You'll get it very soon. And I'll give a solution to homework 1 as well. Once all these ads are over, obviously I don't want to give it out while there's still people adding. Yes?
So for the grader, there would also be section 3.
Yes, never mind that. He made 2 accounts for section 3 and section 4, and I said, who needs it? Okay. Because it's going to be a hassle for him, since as many of you know, when you set up Git for the most convenient way of setting up Git is to make an SSH key without a passphrase, and then you never have to type in your password. And if he now has two different identities, it's just going to confuse the issue to no degree. For no gain. I mean, you don't really care what his name is. The reason that he has an anonymous name is, of course, so that you can hassle him in private about your grades. Yes?
There's I've been in a situation before where you need 2 separate accounts on GitHub or something, and it's there's more than one way to handle it.
Yeah, sure.
It's complicated.
That's the thing. And he's going to have enough complications to deal with. I figured there was no need to increase that. But yes, you can certainly do it. And I mean, you could probably just have multiple SSH keys, and they'll just all get presented, and one of them will work out. But why? All right. So we talked about blocks last time. A block is a thing where you have braces, and then you can put variable declarations in here, and a block has a value, like everything else in Scala, and the value of a block is the last expression. So here you see a typical block. I define dx and dy. Then the reason I defined them is because I needed them twice. Then I have an expression that computes the square root of dx squared plus dy squared. And that's the value. So I can take that value, and that value gets assigned to distance. So this is a typical example on why you might want a block, because we want to declare these variables so that we can use dx and dx again, instead of having to say y x2 minus x1 times x2 minus x1. Could you put 2 expressions into a block? You could. Would you want to? No, I wouldn't have asked, right? But why not?
Then you're ignore one value.
Yes, it would have to ignore the first value, right? If you put another expression in here, that expression can do nothing in a purely functional setting. It cannot change the world. And so whether you have it there or not makes no difference. So in a purely functional program, you would never have more than one expression. You would declare a bunch of stuff maybe and then you would have a single expression. Of course, in an impure program, you might have print statements or something like that, but we're staying in the pure subset of Scala right now. So it's common to do this, particularly when you have a somewhat more complex recursion. So you're going to be needing this in the homework and maybe in the lab. So here I have an example that's similar to what we've done on Monday in the lab. Here I'm computing the sum of all of the digits of an integer. If the integer is 0, then that sum is 0. Otherwise, I compute the last digit, it's n mod 10, the rest n div 10, and then I have the answer to my recursive case, namely it's the last digit plus the digit sum of the rest. And so you just have this expression here. Notice there's no return statement. There is a return statement somewhere in Scala, and I can never remember what it does. It doesn't do anything useful, so make sure that you don't accidentally write it. We'll never have a return because we're just having an expression that computes the answer. All right. Local functions. So you've seen how you can, when you have a block, define values. You can also define functions. So here I'm defining myself a little helper function. And because the scope of this helper function is only from here to the end of this block, I can give it a short and sweet name. Right? It'll never be used anywhere else. So here I square x2 minus x1 plus the square of y2 minus y1. No big deal. You can define functions anyway. Just in general in Scala, Scala is very regular. In general, if you can do something in one spot, you can do it everywhere. So you can define functions everywhere. Unlike in Java, right? You can't define like a method inside another method. So this is particularly useful for recursive helper functions. Sometimes you have a function that by itself is not so easy to express recursively, and you want to have a helper. Or sometimes the helper is better in some way. So I'm giving you a different implementation here of digit sum. That, again, sums up the digits of the integer n. But now it's going to use a helper. So I define the helper here, digit sum helper. And it's a thing that I don't want this thing to be known anywhere else. It's just a helper for this thing. So that makes it perfectly suited to have a local function. Once I've defined it, and we'll look at the definition in a minute, then I call it digit sum helper. And here it is. So the value of this call will be the value of the function. And so you'll appreciate that this is an elegant way of hiding the name of a helper function. All right, so notice that digit sum by itself is not a recursive function, so I don't need to specify a return type because it calls the recursive helper function. The helper, on the other hand, I did have to put a return type. Now, what does the helper do? This is a common strategy for a recursive helper, that it gets the value to be worked on, and then it gets a second parameter where it accumulates incremental work. At the beginning of the call, we give it the number that we want to analyze, and the incremental work that we have is 0. We don't have anything yet. In each step of the recursion, it says, is n 0? That's the terminal case. In that case, the incremental work is now the complete work, and it's returned. Otherwise, we make a recursive call and say, keep working on the rest of the number, everything but the last digit. But now the incremental work is what the incremental work was before, plus the last digit. So in each step, one other last digit gets added into something. Now, this particular implementation of this recursive helper has a beneficial property. It's what's called tail recursive. That means that the compiler can transform it into a loop. So what the compiler will do is, when it sees this digit sum helper function, it will turn it into the moral equivalent of the loop that I've written here. This is, of course, not legal Scala. You can see that it's not legal because here I'm making an assignment to a val that you couldn't do in Scala, and also there is no goto statement in Scala. But this is like the assembly instructions that it, so to speak, is generating. So it says if n is 0, then return sum, just like over there. Otherwise, it transforms n by dividing it by 10, because you see this call here turns into this call. It transforms sum by adding n mod 10 to it. And then it jumps back to here. And it doesn't make another function call. It instead just jumps back to the beginning of the function, and it keeps on going. So it builds a little loop out of this, or what used to be a recursive function. We'll see in a minute why this is a useful thing to do. So you couldn't do that yourself, but you can tell the Scala compiler, hey, I want you to give this the good try. I can't remember what I was saying. I'm sure no one else can either, so I'm just going to come back to it when I remember. Lists, and then we'll get back into the importance of the tail recursion. So we have lists in Scala. They're not really the same as the Java linked lists because the way you work with them. In Java they pestered you with linked lists. In the CS2 course, like 46B, you had to learn how to splice them together from individual nodes and all of that stuff. And if you're like any students that I've ever had, you probably dislike that activity intensely because it is error prone and tedious to debug. In Scala, the lists are not at all like that. They're very easy, they're simple, and there's only a couple of primitive operations that you need to know. So if you have a list, you can get the head of the list, that's the first element in the list. You can get the tail of the list, that's everything but. So you have a list that contains 1, 4, and 9. The head is 1, the first element, the tail is the rest. You can call tail as often as you like until you reach the end, and the empty list is called nil. So a list is either empty, which means it's nil, or it has a head and a tail. That's all that you need to know to read through lists. There's no such equivalent for having like an iterator like you have in Java. Instead, you just keep on calling tail, and you go further into the list. If you need to build a list, you use this operator with the 2 colons that is pronounced cons for historical reasons. So cons takes a list, and you write cons backwards. You write the list to the right, the cons before, and the thing that you want to prepend to the list to the left. Then what you get is a new list that contains all of the elements of the old list. In this case here, 149, and what you put in the front. So you can stick something in front of the list. There's no operation to stick something in the back of the list. If you want that, you have to write it. Yes?
It seems more like a stack than a list.
You could say it kind of seems like stack, but it's called a list. And it's not really like a stack either, because in a stack, when you add something to a stack, you have mutated the stack. Here, when you call colon, you get a new thing back.
Oh, okay.
So every time that you do a cons, you get a new list back. So I said it's easy to program with them, so let me prove that. I give you a couple of functions that should be so easy and intuitive that it's clear why this is a good way to do it. So let's compute the sum of all of the elements of a list. You have a potentially long list, and I want to compute the sum. Well, if the list is empty, then the sum is 0. Otherwise, I take the head of the list, the first element, I sum up the tail, everything else, and I add those two together. That is the sum of the list. That couldn't be easier. Right? If you had to explain to someone how to compute the sum of something, that is the way to do it. Right? This is so much better than what you would do in Java. In Java, you would have to have like a thing that you, like an accumulator, you would have to say I goes from 0 to whatever, or you have to have an iterator to visit the elements. So this is dead simple. Now, what if you need to build a list? That's also pretty easy recursively. So here's, I want to build a list of all of the squares. And so if n is 0, then that's the list containing 0. Otherwise, I compute n squared, and I cons it with the list of all the squares up to n minus 1. So let's say that I do that. I should have put it like a clicker question in here. I forgot. If I compute the squares, oh, sorry, it just takes an n of 3. What do I get? So obviously that's something with 9, 4, 1, and I guess 0, right? So what do I get?
0, 1, 4, 9.
Okay, so you say 0, 1, 4, 9. Do I hear a different answer? Yes.
9410.
9410, and that is in fact what you get because the 9 comes first. When you call squares of 3, it says 9 followed by the list of the squares of 2. So it's 9 followed by 4, followed by 1, followed by 0. Yeah?
It's kind of similar to string concatenation and then the substring as well.
It is kind of similar to string concatenation with one difference. You notice that here I've gotten the squares kind of in the opposite order. What if I want them in the other order? With string concatenation, you can just flip because plus doesn't care. But here you can't flip because colon colon is not symmetric. So you can say something colon colon a list that prepends the thing to the list, but you can't do it the other way around. There's no operator. There's no easy operator. And the reason, of course, there is no easy operator is that it wouldn't be cheap to do, to append something to a list. Okay, let's actually talk about cost. So let's look at the first function. When a Java programmer looks at this function here, they're going to say that is a crazy way of computing a sum. Because if you did this in Java, let's say you did this with a linked list or with an array list, what would that mean? That would mean you take the head element, and then you make another list that contains the entire tail, and then you recursively call the function on that list. So you would have to copy the entire tail into something new. Because in Java, there is no way of saying, give me the tail in a cheap way. But in Scala, to get the tail is cheap. This is the list that it was originally. And then when one computes the tail, then one simply gets a reference to the second node in the list. Now, in Java, one could possibly do that with a linked list, except why would you never do it in Java?
Just use a float?
No. If you actually had a pointer to a node in a linked list, would you give it to someone? It would be a crazy thing to do. Would you give someone a pointer to your liver? I mean, they could do anything with it, right? I mean, they now would have a reference to the internal of some data structure. They could mess up your links, right? And so in Java, because the nodes are mutable, it is super dangerous to give an internal anything into the internals. Now in Java, you could say maybe at least there's some amount of protection because not everyone can access them. But let's say in C++, if you have a pointer to something in there, you can do anything you want with that pointer. And so that would be a total no-no. That's where the iterator was invented. The iterator is kind of a safe way of poking around inside a list without giving too much of the internal implementation. But, of course, even when you give someone an iterator into a linked list, again, they can do arbitrary modifications to the list. The reason it works in Scala is that these things are all immutable. Nothing can ever happen to them again. And so it's perfectly fine to share the internal structure with others. All right. So here are a couple more recursion examples. Again, to show how easy it is to work with these linked lists. So here I have a function called append. There actually is such a function in the Scala library, but I show you how one would implement it, or how one could implement it. So append takes two lists, and for simplicity I use lists of integers here. Notice, by the way, lists in Scala, just as in Java, are generic types. So you have a list and then a type of the elements, and in Scala one uses angle brackets, square brackets instead of angle brackets in Java for no discernible reason. So we have two lists A and B, and append will produce a new list that first contains all of the elements of A, followed by all of the elements of B. Yes?
Quick question about the tail command. When it refers to a list, is it the very last element of the list? And does it...
No, tail is all but the head.
All but the head?
Yes.
Okay.
So if you have we had an example here. So yeah, if this is the list, if LST is 149, then the tail is the list of 49. Notice that the head is always an element, and the tail is again a list. So head and tail are not totally symmetric. And you can think of head and tail as being the opposite of cons. All right, let's try this again. So if A is empty, then concatenating A and B is easy. It's just the answer is B. If A is not empty, then I can take the head of A and append it with the tail. Then I concatenate it, sorry, with the result of appending the tail of A to B. So, see if we can get a marker that actually marks. So, if A is this list here, and B is this list here. Now, let's do the computation here. The first line says if A is empty, it's not empty. But so it now says to take A dot head and cons it with append A dot tail and B. So I'm making a new cons cell that contains the same thing as here. Let's say this is a 1. And then its tail is going to become what? It's the result of appending A dot tail and B. So A dot tail is here. I'm making a new cons cell that has a 2 in here. And its tail is the result of taking the tail of that, which is nil, and appending B to it. That gets me into this case here, where the thing that I feed into the function is empty. And in that case, the answer is B. Now, it's literally B. That means it is this pointer. That's the list that's being constructed. Notice that the result had to copy the cells in A, and then it got to share the cells in B. It didn't have to copy those. It could just take them. Again, sharing is safe because all of the stuff here is immutable. Nothing can happen. That's the best we can do in terms of sharing. We can't share anything in A because A has a nil here that we cannot change. There's no way for us to pick up this cell here for that reason. We have to copy those into new ones. All right. Now, let's see, how would we reverse a list? Well, it's again recursion. If the list is empty, reversing it is trivial. Right? What's the reverse of an empty list? It's an empty list, right? So over here I said if A is empty, I wrote A. Could I have written if A is empty, nil? Yes, no?
No.
Sure, I could have written it, but 2 extra letters. NIL has 3 letters. A only has 1 letter. So that was the only reason to choose A here. Because it really doesn't matter. If A is empty, it is nil. All nils are the same. It's just like null. No one null is the same as any other null. Right? Null is just a value of 32 zeros. So, but it doesn't matter. You can say nil if you find that clearer, or A if you want to protect the keyboard. So otherwise, if the list is not empty, then I have to reverse the tail. So let's say my list was 1729. I reverse the tail. Here it is. And then I have to stick the 1 at the end. That's not something I can do with cons. Cons can only stick something in front of a list. But I just wrote a perfectly good function that can do this, namely append. Append appends to lists, so I need to make a singleton list of the head. Then I call append, and then that's going to stick it at the end. Okay? So let's try that function out. And since we're also unhappy about the Scala IDE, I'm going to show you a different tool. So this tool Oh, I need to. Is a read, evaluate, print loop, or a REPL. It's kind of like the worksheet, except I type in commands or expressions, and it evaluates them for me one at a time. So I'm going to copy and paste this thing here. I need a pen to do reverse. And now it says it's defined this function. I'll define reverse. Here it is. And now I could reverse something. Here, then it's reversed this list. Okay, so that's exactly like the worksheet, except on the worksheet those things show up on the right, and here they show up below. Now, let me do something else. Let me make a very long list. The way you make a long list is like this. You say 1 to 1 million to list. It doesn't show all the values for obvious reasons. How do I know that it really is that long? I can ask it. Res4 is the result number 4, and it tells me it is indeed a million elements long. Okay, so let's reverse it. Oh, what just happened? Yeah, no idea, right? Let's check on Stack Overflow. Okay, so it's a Stack Overflow error because this function called itself recursively. It tried to call itself recursively a million times. Each time you have another recursive call, you have another little record on the runtime stack. The runtime stack is not made to be large enough for a million recursive calls. They could have made it large enough, but they said there has to be a limit somewhere, and that whatever that limit was reached. So that means that this whole idea of saying that every loop can be rewritten as a recursion does have its technical limits, and we need to have another tool in our disposal. And that's where the stuff with the tail recursion stuff comes in. So I'm now going to rewrite reverse using a helper that turns out to be tail recursive. Now let's first of all see why reverse itself isn't tail recursive. So if I were to declare this thing as tailrec, well, let's actually try that. So if I take this thing here and say at tailrec, then it says it can't do it. So it says the recursive call is not in tail position. So the reason is that the recursive call is here, right? Reverse calls itself. And it's embedded in a bunch of other stuff. It's not the very last thing that the function does. After calling reverse, the function wants to call append. And if it's not the last thing, then the compiler cannot do that transformation into the loop. So here's my helper. The helper says, I have the stuff that I still need to work on and the partial result. With that, if I don't need to work on anything anymore because the stuff that I need to work on is now empty, then I return the partial result as the complete result. Otherwise, I simplify my problem. I say, let's only work on the tail, and let's stick the head in front of the reversed stuff. Let's just work through that with a simple list so that you can see that it works out correctly. It's otherwise a little hard to see. So when you have the 1729, that's your A at the outset, and the second parameter is new. Then the helper calls itself with the tail, 729, and it takes the 1 and sticks it in front of the new. Then it calls itself with the tail, and it sticks the 7 in front of what you see here. And you see that it gets built up in reverse order, the way we want it. Then, of course, the 2 gets stuck in here. And then finally, the 9. And at this point, the first one is nil, and the second one is correct. Why is a tail recursive? Because if you look at this recursive function, you see that the recursive call is the very last thing that's being done. There's nothing else that is being done with the result. It doesn't get stuck in another function like it is here. And so the compiler can, in fact, optimize that. So let's try that. So I've pasted this one in, and it was happy with the tail rec. So the compiler has confirmed that it was able to do the rewriting. How do I know if it worked? I guess I can call reverse. Yeah, so it still reverses, but how do I know that it's tail recursive?
It's not really a stack overflow.
Well, I didn't get a stack overflow, right?
I mean, for big.
Aha. Yes, so that's so. If I call it with a big input, then it works, right? No stack overflow. So it worked. All right. That's all. So go ahead and find your buddy. If your buddy is no longer with us, find a different buddy. And yeah, let's go through these. And about 5 after 1, I will stop you, and I want to talk about things. There's a couple of questions in this lab where there's no way that you can know the answer. And I put them in on purpose to see if anyone would raise their hand. No one did in the first session. So I hope you can do better. All right, if I could please have your attention for a few minutes that we go over the things that I want to point out. So it starts out pretty straightforward. What's the type of this thing? And it's a list of int, right? What's the type of when we mix things? Oops. Okay. No. Okay. So here it is. It's a list of any, and that's not something that you generally want. So we're going to try to avoid that situation if at all possible. So now you get an error when you call this expression. This thing is not very fast. Here. And the error is a little curious. It says, : is not a member of int. Why does it say that? Yes.
So we got that too. At first, I thought it was something to do with generated code, but I think it's because it's expecting. Maybe it's expecting nil at the very end.
Yeah.
Well, okay. The compiler is not particularly expecting nil. It's not that it's the compiler sitting there and says I'm hungering for a nil. The compiler evaluates what you write. It has no idea that you're trying to do anything with a linked list, right? So what does the compiler do? It says, okay, I need to figure out where does the : operator apply to. : is right associative. As it turns out, all operators that end in colon are right to left. So then it says, well, if it's right to left, I need to apply it to the 3. And then it asks itself, well, what's 3? 3 is an int. Does int have a : And it does not. So that's all it complains. It says, you've given me an int, you've given me a : as it happens, you write it the wrong way with a : and that just doesn't work. So it's not looking for a nil or anything. It simply says, you've given me something to operate on an int. So that means the last thing in a chain of : must be a list. It could be nil, or it could be some other list, right? So you could do, I could put, a list with some other stuff in here, and then that'll work. Okay? Now, what happens? This is a list. : is applied to that list. The other operand is 3. I'm getting the list 3, 4. : is applied to a list. The other operand is 2. I get a list. : is applied to that list. It just goes right to left. And the reason they made : right to left is, of course, because that way the elements appear in the natural order. They could have done it the other way around, but then they would have accumulated in what seems like a confusing order. All right. that's that. So list function. So when you concatenate these strings here, I gave this as an example for a function that essentially writes itself. So I write def concat. It takes a list of string. It's recursive, so I have to give a return type. What's the return type? String, right? Okay, and so if the list is empty, then I guess I get the empty string. Else I get, well, I'm going to take the head and concatenate it with concat of list of tail, right? Well, I'm not there yet. That was the thing without the space, right? So now we have concat of list I'm not gonna. She just added lamb. Doesn't have to be little. Okay. So, and here, then it doesn't concat with the space, right? So how do I get the space? Can I just put a space in here? Well, then I have an unsightly space here at the end, right? So how do you solve that? Aha, so you made another case. So, yes, absolutely. So you could put another case in here and say else if list tail. You said if it's not equal nil? Okay, what?
No, we just use if and else.
Okay. Well, if it's nil, then it's the then it's the head, right?
Yeah.
Okay, let's try that. And there we go. Okay. Notice it. It's a little hard to see now. IntelliJ did not put the double quotes. Apparently, IntelliJ will put them when there is a trailing space to make sure that you see it, and otherwise it drops it. It's kind of a nice touch. We really want to know that that's correct, we can compute the length, but I'll leave that to you. So this is the easiest way of doing it, to add a separate case. Now, in the interest of time, I only have time for one more thing here. So I'm going to skip this thing with the pairs, and I want to go to this thing with the squares function. So we had a squares function in the lecture. Here it is. And so the squares thing was done recursively. And now your challenge is to do it without recursion. So how can you do this without recursion? How do you rewrite squares without recursion? You can't write a for loop, Scala.
No loops.
Like math or something, but doesn't that internally do something?
Well, we don't care. Map, for all we know, is written recursively. We'll write map next week, and you'll see it's a recursive function, but that's okay. No, but this is what a Scala programmer really would do, is we would want to use map. Map is always the first go-to tool that you try to use. So in this case, we would use map. Well, quite clearly, we want to map the squaring function onto something, right? So we want to get the list of the first n integers and then map. How do we get the list of the first n integers? We did this in the console. Excellent. Yes. So the way you do it is you say 1 to n. I'll just do it with 10 here right now. To list. And that gives me that list, right? So then I can map it. And how the mapping is just with the squaring function here.
What's a range?
It's a thing. It doesn't actually a range doesn't actually store all the numbers. It just stores the first and the last. Whereas the list contains them all. Okay, so now it's bad REPL day. Okay, I'm just going to use my thing.
The question was implementing square without recursion.
Yes.
Use map.
Yep.
Map, use recursion.
We don't care.
Okay.
We don't care.
It's not our breakdown.
It's not our, exactly. That's exactly the right point. So I'm going to use this other REPL again. For some reason, this one froze too. Okay, so here you can see how the squares work. But it's not quite the right thing, right? I need to start at 0 to get the same effect. It's not quite the right thing because the other one was in reverse order. How do I get them reversed? There seems to be a lot of functions that I can call. One of them is called reverse. There you go. That's how a Scala programmer would solve this. So as a Scala programmer, you would not use recursion for something like that. If you can use map, map is always considered to be a better and more convenient thing because it is better and more convenient. Right? Remember, we didn't do the recursion because we love recursion. Of course we love recursion, but no, we don't really love recursion. Right? It's just a tool. We did the recursion because that was the only thing we knew how to do. So if you can use map, it's the thing that we know how to do, then by all means use map. So it's not a sport to do everything in recursion. You want to do it in the most convenient way. And so a Scala programmer will always try to use one of those what's called higher order functions, such as map or filter or reduce or fold, before attempting a recursion, because a recursion is more hands-on, more primitive, more low-level. And so if you can do it better, by all means do that. I'm saying that now because the homework assignment now is for you to do a bunch of recursion. And I don't want you to get the impression that that is the go-to tool. One time I had the chance to look at the solution of 15,000 students who took a Scala MOOC from Professor Odersky. And he gave a large number of exercises, and it turned out that over 90% of the students used recursion all the time because they previously probably had a course in Scheme or something. And they never learned the higher level tools that Scala provides, which makes you wonder about the value of a MOOC like that. But whatever. So recursion is a necessary tool, and I want you to get good at it, but I also want you to realize it's not the first thing that a Scala programmer normally does. All right, that's all I have for today. So there's